Okay, this talk is a bit more technical. So, but for those that actually want to see a little bit of math, it's there. But hopefully, I'll manage for you to get the gist of it, so the fundamentals of it, and then for some additional details you can ask me and so on. So as always, let me thank the collaborators here. So these are those who actually involved in all of these papers that I'll mention. Deborah Das was actually a postdoc, was there for a year and a half only, not the usual 2-3 years. Dan Maris, Tobike, and Siralan Sarvaharman. So they're all PhD students. So the last two that finished, Dan is completing now. So, so let me thank them first. Okay, so what am I going to tell you about? So, since you'll see discrete math, I've taken everything out of continuous. There is no continuous math. So I should actually ask the question, why on earth should we do that? Should we learn it? Are there advantages? And my hope is that by the end of the talk that you'll say yes. Okay, I'll query you then at the end. So I'll start by telling you what are these discrete objects, which are called lattice random walks. You heard earlier I talked about random walks. So that was a more complex problem. These are simpler problems, but they are still random walks. And they are lattice because they are in a discrete space. And so I'll tell you about those. And they are Markov. So there is no history dependence on the process as it happens. So maybe I should just move this out of the way. Oh, so much easier. So I'll tell you about the process, a concept and the mathematics associated with it, which is called first passage, which is crucial in all that I'm going to tell you. So all these advances that has happened in the last few years, it's about answering those questions which are related to first passage process, first passage statistics. So that's a part, a little bit of math that I'll have to teach you, and hopefully I'll be able to tell you, I'll be able to explain so that you understand. So, and I'll distinguish when you have reactive interactions and inner interaction. So inner interaction is when you're disordering space. Reactive is that you react in somewhere in space with an object. Yeah. And then I'll show you that these techniques do not have to be on lattices, which are regular lattices. They could be on hexagonal, triangular. I'll give you some example that you can actually do the math. And I know some of you in the audience know already about this crazy phenomenon. So those of you who know cannot talk and say, because I'll give you a quiz on that to see what the audience says. But those that know cannot talk. So I had to come up with a name. I call it disorder indifference phenomena. So yeah, okay, you'll see why. Then I'll just mention that these are all the Markov, because I say at the beginning, but actually we started working on no Markov process. When you have a persistent movement, which is a movement for which you have a higher tendency to keep going forward, so it depends where you come from. It's a one-step no Markov. So I'll tell you that what we can do on that. I'll briefly mention multiple non-interacting individuals. And then this is what we started working very recently, even on networks. If you had random walks on networks, now the lattice is completely irregular, no? So there is no lattice. And so there are interesting findings that, it's, people in network, big literature network theory, it's not there. So in other words, so this, it's a very versatile tool that I'm going to tell you, and it comes back to the why on earth should we use discrete? And you'll see the results should, convince you that you probably should learn. Okay, anyway. So, okay, let me start. Well, to answer the question, why on earth, should we do that? Maybe let me tell you why people have used, instead of answering that question with that, you should answer that question, but why people have used continuous for so long, no? So why it's actually predominantly people use continuous. Well, so why it has been so successful? So I pick the simplest example. Everybody knows this equation, a diffusion equation, no? You know what diffusion does, no? You put something in space and then over time, its location gets pretty much, you have equal probability to find it anywhere, no? So that's what diffusion does, no? So now, so it's easy to find a solution in time and space. So, and that's, once you have an analytic solution, it's very convenient. And this has been solved in 1D at least, also with all sorts of boundary conditions. So this is just to show you, sorry, this came up before that one. So you have a generic condition you can apply. So you have a gradient here, you have a coefficient kappa plus, kappa minus, and the value at a specific location. So this should be at A, sorry. And so then there are the normal boundary condition, Dirichlet. So depending how you choose those parameters, 0, infinity, and so on. And since I mentioned to you at the outline, there are inert interaction and direct interaction. So I'll go in details what it is. So, but there are specific meaning to that, even in continuous. Okay, so in 1D, this has been super successful. In 2D also, we know it, diffusion equation in 2D and so on. But once you start going to higher dimension, you have multiple boundaries. There is no analytic solution in continuous. Yeah? And so now you should understand why you should learn about discrete, because you have analytic solution in discrete. Yeah? Okay, so let's see the usefulness of that. Okay, so now let's think about the classical random walk problems in 2D. So remember, the exact equivalent of a diffusion equation is a random walk on a discrete lattice and discrete time. It's the exact equivalent. You make the limit of the lattice going, distance between lattice point going to 0, time becoming continuous, then you get the diffusion equation. So we'll discuss about that. And what are the process problems that we actually are interested? I mean, these are classical problems. It's not just biology and all sorts of subjects. Is that you have something that moves randomly. It's like you think about someone, as a blind, he's covered his eyes, and then you have some escape. This is an escape problem. There are some location which you should find, by which you should get out. It could be an animal chased by a predator. No? So once he gets, that's a refugee place. So there could be more than one. No? So you might be interested in finding out how long does it take to get there. So a very similar problem. The only difference is that those special places, instead of being at outer boundary, they are all over, is a foraging process. Within a certain time, you better find food, otherwise, you die. No? So then the time scale in which you find the food, it's important. So therefore, it's another classical problem. So earlier this morning, someone asked me about COVID. Yeah. So this is, what's the difference between this and this and this? No difference. It's the number of locations where the interaction happens. Yeah. I draw it for you. So this represents two animals, one in this space, the other one, they don't share all the same space, but the one that they share, that's the one where they can meet and they can pass something, an infection or, since we are talking about, So what's the difference? Nothing. It's just the number of elements which are special, correct? Okay, there is a different geometry, but that's, So another problem that is important, when I mentioned disordering space, we don't live in a homogeneous space, no? So we always move in some heterogeneous space. And so this is an example. You have a random walker, and here what I'm pointing out is that this is a permeable barrier. I mean, going through here, there, is different than going from here to here. This is a fully reflecting barrier, I think. That's an impenetrable, that's a fully reflecting barrier, but in the middle, not outside. And this is a region where your diffusion constant, which in discrete lattice is called diffusivity, because it doesn't have units, that's okay, is different. So these are all heterogeneous space characteristics. So again, these are all the sort of problem people are, and then you can have this onto this problem. Now you have the COVID problem. Or you can have this into that problem, and you have animals searching for food in their environment and so on. So it's very modular as you look at this. All that matters, there are special points, lattice points, for which you have to decide how to model the interaction there. So these are the ones that are reactive interactions because you don't conserve probability. As you reach one of these points, your state, for example, infection state, has changed. Or here you get out of the system. So it's like an absorption point. So that's why the reactive. So once you get there, there is a chance of you getting out of the system or changing. And this, on the bottom right, these are the inert interactions, so your probability is conserved. So there are two different mathematical techniques you have to use for the two, obviously. So again, they don't preserve probability, they preserve probability. Yeah? And so all of these special points in the literature are called defective sites. you have defects, but defect compared to what? Compared to whatever you know to be the problem you're looking at without those. Huh? Yeah, okay. So you will hear me say defects in that context. So, okay, let me skip that. So now let's look at a bounded space. It doesn't have to be, but let's look at bounded space. Yeah. So, and let's write now a little bit of math. We all know about the diffusion case, since I mentioned that it's exactly equivalent to the lattice random walk. What's the discrete equation for diffusion on a lattice, the discrete time? So imagine you have your lattice point, and you enumerate your lattice, position, and you are interested in describing the dynamics. So probably you see, yeah, maybe you see, of the occupation probability at location n as a function of time t. Same as p of xt when I showed before. This is just discrete. No? So what's the equation for that? You describe, now, since it's discrete, you have t plus 1 instead of a derivative. The probability of being an n at the next time step is given by the probability that you are at some of the other location m, wherever they are, as a function of time t. Notice that it's a time t, not t, just t plus 1 to t. So that's why it's Markov. And this transition, now in this case it's 1D, it's a matrix, then they define, are defined as what you saw in the drawing. So you have a chance to go from n plus 1 to n, q over 2, q is a parameter in 0 and 1, then the other n minus 1. So this, in this case, this is, for that example, it's 3 diagonal. No? It's a 3 diagonal matrix. Huh? So the rest is not there. So in fact, you can expand it out. Probability of staying is 1 minus q, p at same location. And then you have a chance q over 2 to go from left to right and from right to left. Huh? Yeah? And this is for any n. No? So that's the exact equivalent of the diffusion equation. So let's assume you have reflecting boundary. I mean, you don't have to, but otherwise you get an integral. But anyway, you get a reflecting boundary, and so you solve that equation. And then you can ask me later how you solve it. But in time, so this, the symbolism that I use, this is the initial condition. So you start at location n0, wherever it might be, at position n as a function of time t. It's given by this object. Remember, you have capital N number of total sites because you are in a box. So this is the number of total sites present. And then you have your dynamics is in here, no? So if you put T0, you will see this is essentially gives you a Kronecker delta at N0. So everything is 0 except at N0. Yeah? But over time, eventually this, because you are equally likely to be anywhere in the box, this term goes to 0. Yeah? And so you're left with only that term, which shows you in fact that you conserve probability, also anytime, but also a long time. Yeah? In fact, if you want to know more, so what is the shape of these quantities? They are very simple function. No? These are cosine function that depends on n and n0, and you're summing over k. Yeah, it's a sum. And this sk is essentially, if you think about the symmetric form, it's the eigenvalue. No? So that's essentially what that is, the eigenvalue. So skt, then you see it's like, you still have cosine, the k function, then it's to the power t. Those terms are always smaller than 1, so a long time it goes to 0. Yeah? Simple. So this has been known for a long time. 1D, these results were known. Okay? So, now let's come to the 2D case. Yeah? And so the fundamental reason why people have not studied this problem is because in continuous, that sign is equal. Yeah? Just think about a Gaussian in 2D. It's a product of Gaussian in 1D, no? In discrete, it's not. So this is the key part. People have not really used it. They didn't know how to solve it analytically. And it doesn't matter. It could be unbounded or in a finite space, no? And that's what was missing from the literature. How do you go about, in higher dimension, to finding this occupation probability solution of the equation? And this is the paper that started all this business. So where that solution in any dimension was found, and to some extent in any boundary condition. Yeah? So, and this I'm just showing you the example for the 1D case. These are the periodic, reflecting, the mixed boundary, this one, and the absorption. No? So in 1D were known, scattered in the literature, but higher dimension were not, except the periodic case. Yeah. So, okay, just to give you an example for the 2D version, so things get a bit more complicated. So imagine if you have a box, reflecting box, and you have a bias, which is essentially a bias going down the bottom left corner. So it pushes you down there. So now, in that case, now you have a bias. Now it's a bit more complicated than before. So now, you know, without going too much into the details, but now you have a position which depends on n and m. So you have two coordinates. At t plus 1, everything that comes here depends on t. And then, you know, this is the probability of staying like it was in 1D. But now you have a bias, G1, which is along that axis, and the G2 is along the other axis. And notice you come from the left, you come from the right with a given bias. Yeah. So G1, when it's 0, becomes the diffusive case. And then here you come from below and you come from above. No? So again, okay, in unbounded space, it's easier to solve, but in bounded space, it was not known, essentially. So just to show you, when you go in and solve the problem, now you get a double sum, which depends on K and R. Yeah? One depends on K, one depends on R. But now you can see why they're not the product of two one-dimensional Ks. As you sum K and R, S depends both on K and R. It's not the product of SKT, SRT. In that case, it would be a product 1D. So it's the combined element. In fact, if you want, so in this case, H is horrible. I'm not going to show it to you. But SK, now you can see, no? So K and R are inside this to the power T, and you have K and R here inside the cosine. Yeah? Okay, so this is just to give you an example. So if you want, you can easily plot this object. Imagine if this is a G which comes down this way. I mean, the initial condition was probably around here, and then it's what's the time scale here? That 10 to the 3, okay? So then, you know, you need like the fraction of a second to plot this, no? Okay, so now let me come to the important part of what you use this for. Because besides plotting occupation probability, what are these questions? These are the questions related to the first figures I was showing you. There are special points in the lattice for which you want to ask questions. How long does it take to get there? Yeah? And you will see, I want to show you, and then we go through the details, that you need the occupation probability, which now we have. Before only in 1D. Now we have in any D. In any disordered space, in any network, so it's like in anything, okay? So, but before we were taken away by the enthusiasm, let's go in and understand what we mean by first pass set. So imagine you have a searcher and a target position. So the searcher moves randomly, has to reach a target, which is fixed. Yeah? So I just present that with R0 and R, yeah? Searcher and target. So imagine that, remember, this is talking about random walk. So that searcher starting at R0 moves in a random way and eventually, well, if it's a finite space, will hit it. No? So eventually hit, R. So those, zigzag arrows represent random movement at some point. No? So how do you represent, in this context, how do you link the occupation probability to the first passer's probability? So what's the first time for which you reach from R0, R? It's the first time, no? Not any time, the first time. So I want to relate the occupation probability that you start at 0, you reach R, and it's a vector because it's any dimension at time t, and I want to relate to the first passage to go from R0 to R at time t. That's clear? The first time. That's, yeah? And notice, this is the same time, no, sorry. I want to relate to the one at earlier time t prime. So that's the reason, sorry, I forgot. I want to relate to something earlier, yeah? So on the left, I have time t. On the right, I reach there at some earlier time t prime. But for the first time. So I reach that, and so that's essentially what I'm trying to represent, that at some earlier time. Now, suppose that I've reached that at some earlier time, and now those blue zigzag arrows, then that's what they represent. Now I start at R at some time t prime, and I want to relate that I'm going to be at time t at r, no? Correct? So remember, I've reached there some earlier time, and then I go about my random trajectories to come back at time t at r. Huh? Yeah, so I come back there. So I start at r at time t prime, and I come back at time at r in the distance between t minus t prime. Huh? Given its Markov, then you can make the product of this probability that you reach with the probability that you start at r and you come back at r in the difference in time. Huh? Yeah, so that's what those blue arrow means, and that's why I draw it blue. So this represents all the trajectories for which you start at r, you come back at r in the difference. Yeah? Now, what's the time t prime? It could be anything, no? Yeah, it doesn't have to be. So you sum over all possible t prime. And so that relation now is between the occupation probability, which we now know, this other occupation probability from two different points, if you want, and the first passer probability, which is what we were after. Yeah? Now, it seems complex as a relation, it's convolution, no? But you probably know Laplace transform, correct? There is a version for the discrete, which is called generating function. So if you apply the generating function on the left and on the right, then you get a product. Yeah? That's called the renewal equation. No? So it's a famous, object. So what's the generating? So it's a discrete Laplace transform. You multiply z to the t. This is a complex variable between 0 and 1. You sum over all your t between 0 and infinity. That's the symbol tilde. That's what it means. You have a generating function of that. And now you are operating on time, no? So you're not changing anything here. Just, it would be tilde of z. So you operate on that. And you have a product of these two because of the convolution property. And so you just divide this one by this. Voila. You have the first passer probability from R0 to R as a generating function. Now you can see, I was telling you, if in higher dimension, we don't know what these one are mathematically, analytically, then we don't know much what to do, no? But if we do know, and we do know now, then you can answer all sorts of these questions. Yeah? Is that clear? Yeah? So now you can show that if you want the mean time of this quantity, the mean of, so remember, this is a probability, so it's going to something, as a function of time, goes up and then down with area 1 over time. So if you want the mean values, then you actually don't even need to find the time dependence. You don't need to invert this. You just differentiate and you put Z1. So it's also convenient in that sense. Okay? Okay, so this is just to tell you about that. So now, but I have many targets up there, no? So what can we do if you have many targets? Well, of course, I'm telling you now that you can do any number of finite targets. So, and the way this is a bit involved, let me skip it, but you can do and find out, let me just give you you can generalize this. Let me come to the answer. Suppose that you are interested, you have two targets, you want to know the first passer probability to either of the targets. One is at R, one is at R prime, starting from R0. And this is the beauty of this transport problem, because you reduce always this transport problem to something where there is one target or there are no defects and so on. Yeah? So that's why you need the probability without defects. Huh? So what I'm showing you here is that quantity as a generating function is given by this divided by that is what is called the splitting probability. It's the probability that you go to one target and not the others. Yeah? And you sum the quantity that you go from this one to R prime and not the other one. And the sum gives you conservation probability. Yeah? But now, the power of this technique is that you only need the first passers to one target. Yeah? Notice, this is a first passer to either of two, and this quantity are made out of first passage from R0 to R, from R0 to R prime, from R prime to R. See? And those F are easy, yeah? So you build up to any target made up of this individual single first passage. So there is always one target on it. Now, if you are thinking that, oh, but this makes sense, no? There is this, intuitively, I go from R0 to R, then I subtract all the trajectories that go from R0 to R prime, and then I go from R prime to R. That's intuitive, yes, but you're overcounting. And so this denominator, only if you solve it analytically, this denominator is the one that allows you to not overcount. I mean, there is no way to guess it. You have to solve the problem. Huh? So now if you want, as I told you, you can compute mean first passage time. So you take that, you differentiate respect to Z, you put Z1, and then you get a mean first passage from R0 to either of the two targets. And now it's like, if you look at the expression, there's like no way to guess it. I mean, you are multiplying first passage from R0 to R, from R to R prime. You are even subtracting things, and you divide by that. No way to guess it, no? But this is the exact answer. Again, it's always the first passage between 2 points. You can have lots of targets, but it's always built up from mean first passage between 2 points. So, okay. Now, one more thing that this is relevant to people that are interested in infection transmission. So far I was telling you the targets which are special, which are the reactive targets. It's as if they are fully absorption. So once you reach them, the process ends, because that's what you need to count the time it takes to get there. But in many instances, you may reach it and there is no reaction that occurs. There is some probability to happen. So how do you account for that? Now, and this is to want to show you, and for just one target, you can do for many targets. So I want to show you that there is a sort of an assumption that people have been carrying out for many, many years about if you have a partial reactive target and you have a searcher, there are two timescales which are important that allow you to give the answer. The time it takes for you to get absorbed by the partially reactive targets. And then, so the belief has been always that if you consider you have a rate, which is the time it takes for you to get there, and then you have a rate for which it's a reactive rate at the target, so you simply sum the two. Yeah? So this is a well-used assumption, even in quantum mechanics, if you know about Mathesian's rules and so on. It cannot be so wrong, okay? It cannot be so wrong, except as you can see here, in some limits, no? So what are those limits? Yeah. Well, if it takes, it's emotion limited, the slow process is so slow that all that matters, is, for you to get there, So that's the emotion limited case. And the other limit is reaction limited. You are so fast to get there, you're always there essentially, but it's so slow for you to react, and therefore you have this other limit. So in other words, this is valid only in the very limit of motion limited reaction limit. But this has been always used, around. So since now we have an exact approach when you have partial reactive target, multiple partial reactive target, so we essentially prove that this is completely wrong, no? This is this belief. Okay, so now without going through the details, just to tell you, if you have multiple targets, which are M targets there, each target has some reactivity, which is not 1. So it means you get there, you may not react. And then if you ask the question, what's my probability that I react, that I get absorbed from any of those M targets, just to show you it's analytical, so you have to compute a ratio of 2 determinants. Yeah? And what are determinants? The determinants contain first passage, the numerator contains the first passage from the starting location to any of the other targets. And the denominator, which is, it's both numerator and denominator. And then you have the first passage that I was telling you about, which are, I didn't write them here. They are inside here, okay? So, because this is F0, which is the top, they are inside here. And they are the first passage between all the targets, permutation of all of them. So 1 to 2, 2 to 1, and so on. They're all inside the determinant, yeah? So in other words, you compute this and you get the generating function, so the inversion is a 1D integral, so trapezoidal rule, and then you get your time dependence. Okay, so then you can compute the mean and so on and so forth. So I just want to show you here, if you want to compute the mean first passage, now this case is 3 targets, yeah? I have 3 targets, I'm moving the coordinates of 1, and I'm just computing the mean. So this is the exact result through that expression, if you want. Yeah. And these are 10 to the 6 simulation. They have not yet converged. It's a 4D space, lots of empty space. So if you try to do simulation, so after we got 10 to the 6 realization, you say, okay, I'm sure if we go to 10 to the 7, we get an answer, no? And we waited, and we didn't change anything. So this is the value of their ability to compute analytically. Simulation cannot even reach there, because, you just barely, getting there. Okay, so, and I don't know who asked me for this transition. I forgot if, yeah, you are still, you asked me. Now, since we are talking about the transmission problem, no? Now, what happens in that? What is different? Nothing. There are lots of targets. So in other words, you have imagine two individuals moving. One is infected, one is not infected. When they co-located, they meet, and there is a partial reactivity, if they pass it or not. So that's the same because, if you think about Markov, it's the same as these two individuals in a 2D space. They're actually in one individual in 4D space with fixed targets. What are the fixed targets? Are the co-location in the previous space in 2D. Yeah. Now it's the same problem. Yeah. So, and in fact, I just want to show you. So, if you actually think about again this problem with two individuals, one infected, one not, the time it takes to pass infection for the first time is so one is the periodic boundary, which is the red one, and this one is the reflecting case, and they start at the opposite corner. So the periodics, essentially are nearby. No, that's why it starts before. And here is when it's perfect reaction. And this is the characteristic when you start having slow reaction. So you have, these curves start flattening because, it's equally probable over time, except when you decay very quickly at the end, okay? So actually, to get a better intuition, I think I have a movie here. Yeah. So again, this is the periodic boundary condition. This is reflecting. So these are the starting location. These are the curves of the overall probability for the two cases, so it's periodic reflecting. And you will see that here I give you the so-called splitting probability, so the probability that you are passing the infection in one location and not the others. And so you'll see that we light up initially here, and for this one we'll have to wait when you come here because they have to meet, otherwise they don't meet, no? So I think if it's going to work, yeah. So you see, they light up here because that's where they can meet, they pass the infection. And then this one, nothing happens until you reach there, then they start meeting there, yeah. So this is the sum in space of all the splitting at that specific location. Okay, so talking about R0, since people didn't know how to compute R0, probably you get frustrated, you got frustrated like me, you go in front of the supermarket and they say, oh no, 27 inside. So why not 28, 30, or 25? Who decides that, no? So it's about, how often you can encounter the individuals, no? So I decided, okay, let's compute R0 for that case. And in fact, it's very simple because you have an analytic answer. You don't have to do simulation. So I just want to show you. So you take that object, which is made out of this ratio determinant. The targets location are the one I explained. They are fixed targets because you go in a bigger space. And then you plot it as a function. This is plotted as a function. This is an SIR model. So the gamma is the rate. Either you get out of the system, the infected fellow, or your infection decays. It doesn't matter how you want to. And so these are the meshing of the simulation. No? So in other words, you can do lots of things in the infection studies and so on. So, okay. Let me skip that one because probably, by the way, what time, where are we, time?
It's fine. You may have 15 minutes.
Okay, let me skip that. So, since I mentioned inert interaction, yeah? So that's the movement in disordered space. So remember that now we have the solution of the unbounded, the bounded case in this lattice without all this disorder, no? How do we consider that? Yeah? So it turns out that in this case, you have to worry about there is no reactivity here. It's only the question about all this transition rate that you are changing between in and out of those special points. These are just disordered. So, and okay, I skip the derivation. I'll show you what I want to show you. I think I have it here. Just to show you the power of the technique. So you can account exactly in an exact manner for that. So this is an example of heterogeneous space. So then you have areas which are completely excluded. You have barrier. You have local biases, which means that if you are here, then you have higher chance of going there rather than going left, right, or down. So this is highly heterogeneous. There are exactly, since I mentioned defects, 177 defects. So how do you compute the occupation probability? I mean, it's like that determinant that I showed you quickly go through. You haven't seen it. Like 30 seconds. 177 defects. This is exact. So you have to compute this ratio determinant. You invert the generating function. So if you want to do simulation, I'll come back next year. You haven't got the right answer yet. So this is just a different time. And now, what is interesting about this, you can also put on it the reactive targets, no? Because we talked about if you know the exact occupation probability, then you can put many reactive targets. This is precisely what I'm going to show you now. We are interested in finding out, starting from there, what's the first pass probability to reach here or there, or maybe one and not the other. Yeah? And I'm going to plot for you. So this is N1, that is N2. So what it means is that, as you can see, to reach N2, it's a bit more advantageous because there is a local bias that takes you there. And then if you see what's your probability that you reach N2 and not N1 is essentially the same as the total, nearly the same as the total probability. Yeah, you see? If you sum the two, that's the splitting, that gives you that. No? But this one is much lower probability. So depending on the problem you're looking at, it could be very important. Okay, so I'm going to skip this one. You can solve in honeycomb lattice because I see the time, because I want to have fun with you about this. Okay? Again, those that know cannot answer or make faces. Now I'm going to tell you something for which I don't have all the answers. It's intriguing. So imagine that this is one of those inert interaction. So you have a reflecting barrier here. You have that one represent a permeable barrier. Means that your chance of going through compared to when there is no permeable barrier is maybe smaller or bigger, depending on what you want to do. So let's say not anti-barrier, it's higher chance. Permeable barrier is lower chance. Let's talk about permeable barrier. Then you start here, and you're interested in finding the time it takes to get there for the first time. That's to the right. But, you have to worry about all trajectory they also go through, no? And come back. So the question is, the mean time, just the mean time, to reach from N0, N, based on where you put your permeable barrier, is it going to increase or decrease? And I'm going to help you a little bit to think. So if you put it closer to N0, then some of the early trajectory, they get pushed immediately to the right, no? Because you reduce the chance of going to the left, no? Correct? So you might think, okay, then it's going to be reduced. I reduce the time it takes, yeah? But there are some cases that once it goes through, if you're very close to N0, there is lots of space where they get, quote unquote, trapped, no? Yeah? So that may increase your time, no? So any guess? Which one wins? None. It's actually independent of where you put the barrier. And some of your face should be like, what the hell is he talking about? Okay, it's just the mean. The probability will change, yeah? Just the mean. So, I can do the math. I can tell you exactly what the formula, I can tell you. But fundamentally, I've not yet understood why. Yeah? So, and that's why we just call it phenomenon because we didn't know what. So in fact, you can show that depending, well, of course, if you put this when you start here, it does affect it. But just because it's to the right, that's why this one is 0. So this is the same as if there is no barrier. Wow. Yeah? In fact, if you put it to the left instead, it does depend where you put it. Huh? So there is also something we found in 2D, which I'm not going to tell you. But I just want to show you. If you look at the probability, these are all different values of the distance from the initial condition. That arrow is a mean. It's exactly always the same. But the probability does change, And this, if you put it to the left, on the other hand, the mean goes from this value to that value, So, okay. So I think, so I'm going to skip the 2D version. Let me skip the correlated. I want to show you, because let me just skip that. You can ask. Yeah, so these are experimental data. We looked at this one, and then I finish. Now, I told you that no matter the disorder, you can solve the problem analytically. You can find the occupation probability. Suppose that now a very simple network I'm going to create, yeah? I mean, again, I give you the simplest example. So I have a ring of sites where you have jumps between, it's not just nearest neighbor, it's also next nearest neighbor. So you have K, so connection to the next, the one to the left, right, and also the one farther left, farther right. Okay, doesn't change much, but, and then I'm going to ask the question, if I start with the green, I mean, I hope you see there are some arrows that connect some distant site. Do you see the yellow arrows? Hopefully. No, you don't see it. Okay. So there is an arrow, yellow arrow that goes like this. There is one which is there. The one in graph 1 probably is the more visible. And then graph 2 has lots of yellow arrow there that connect. So now I sort of go and try to create a network, no? So I'm connecting this, So now if I ask the question, what's the first passage to go from the green to the red? Now, if you think about it, there is a normal time without the defects, which that's a defect also. Yeah, some time it takes to get around and reach, no? So that's a diffusive time scale that you need to get there. But if I put some shortcut, because that's what I'm doing, especially the shortcut is near here, near the initial condition, and then it takes you next to the target, then I'm going to expedite the process, no? So the first passage overall will be faster but the first passage is a probability, yeah? And probably you've seen all the graphs I showed you, then pretty much you have one peak and then it decays. And the surprising aspect of this, if you choose to shortcut so that you're close to here and close to there, instead of having one peak, then you get a double peak. Why? Because there's a time scale for you to take the shortcut, for example, this one, and there is the other time scale, which is very different, which is going around the entire ring. Yeah? So this is something that we have been studying. So this is the graph 4, which you see as a pronounced double peak, because there is this one which is close to that one. And then the graph 1, you see the graph 1 has a shortcut, but it's not too close to the initial condition. So you lose a bit the effect, or you start losing the effect. And then, as you put the other one, for example, this one is so close to the endpoint, and so that doesn't make much of a difference. So, okay, so essentially, I give you an overview of all the power of this technique. There are lots of references. The last one is the one we are working on it, so we haven't finished. But I think we are going to revolutionize a bit, the literature on network. But okay, thank you for listening.